In this video, I introduce the limit of the function formally, and I give you the limit laws, which is a way to go about finding the value of the limit. So, to give you an example, there's plenty of times when we are interested in calculus to investigate the behavior, the outcomes of a function when you're near a value, not when you're actually at it. So as an example, let's consider what's the behavior of this particular function when x is near 1. Well, one way to go about tackling the problem would be to, instead of just start plugging in numbers, let's go ahead and notice that you can factor the numerator of that function. And since x is not 1, that means x minus 1 actually never is 0. So the factor x minus 1, both the numerator and the denominator, represent real numbers that are not 0 and are common factors. Because they're non-zero common factors, I can cancel them, giving me an equivalent way to write the function, which is x minus 2. Now they're equivalent. The functions are equivalent only if I don't change the domain. So even though in x minus 2 you can say, hey, I can evaluate that at 1, you're not allowed to. So the values of the function can really be described by f of x equals x minus 2 as long as x is not 1. This seems to imply then that I can force the values of x minus 2 to be as close as I want to -1 as long as x is sufficiently close to 1 itself. This seems to be borne out both by this table and this graph. In particular, please look at the point where x is 1 and the y-coordinate is -2. If you then look at a point on the graph, that's where the x-coordinate will be x, and the y-coordinate will then be the function value at that x. If you look at this particular sequence of x values and look at what happens with the point on that graph, as the x were to decrease, the point on the graph would move towards the left and ride the graph, much like this. You should notice that as it does so, that the corresponding function values are all approaching the same number. They're approaching the y-coordinate of the point I did in red, which is -1. So it seems reasonable to say that the function here has a limit value as x were to approach 1. Okay, we've talked about this limiting value enough times that we deserve a definition of some sort. This is the informal definition because it still uses some words that don't really have meaning outside of context. So the informal definition of the limit, the way you should talk to people who don't know any better. Suppose that you have a function that's defined for all x in some open interval containing a, except possibly at a itself. So it's defined for values a little bit to the left of a little bit to the right of a, and it could be defined at x equals a or not. We don't care about that. We'll say that the limit of the function as x approaches a will equal the number L and write the notation you see here, provided the following is true. The values of f of x are arbitrarily close to a single number L if restricting x sufficiently close to a. This implies then that we can control the function values to be as close as we want to a single number by restricting x to be a interval of numbers around a, except that does not need to be true when x is a itself. In that case, we just ignore that value entirely. Notice that the limit requires a couple things. The function must be defined around the x value, or there can't be a limit at all. Also, there must be a single number that the function is getting close to, or there can't be a limit at all. Understanding a limit is fairly important for calculus, but most students don't really get it for quite some time. So there are 3 small steps we take you through to get you closer and closer to a deeper understanding of it. The first one is the numerical technique, which says, let's just assume that we know the limit actually exists. So it does, the function values approach something, and then we'll use a finite list of numbers to guess at what the limit value would be. Notice I put that in green because it's not a proof. There are all kinds of problems with this technique, but it's a lowest level of understanding. The next level would be the graphical technique. In this case, you graph a function. You assume you have a well proportioned representation of the graph of the function. You then look at how points on the graph would move and go towards a certain line. And as it goes towards this line, you look at the corresponding y values. And then from that information, you guess at the limit value again. Again, notice this is guesswork. This is not proof. Neither of these can convince anyone of anything. But it does give evidence of limits not existing, but it's not a proof of it. The third and final method is the analytical technique. This is where we use algebra or theorems to prove what the actual limit value would be. The lowest level of understanding is called the numerical method. It's so simple. All we have to do is make some truly ridiculous assumptions. So, for example, we assume ahead of time that we know the limit exists. And second, we assume that from an infinite number of possibilities that we can divine the limit value by looking at only a finite list of values. For example, suppose I want to know how does the function the sine of x over x behave when x is near 0. So I'll assume that there is a limit ahead of time, and I'll assume that if I look at a finite list that I can guess at what that limit would be. So here's my chart. I just picked a bunch of numbers that are getting closer and closer to 0, and I'm looking at the corresponding function values. So you can notice the x values are approaching 0, and it seems, by guessing, that it looks like the y values are approaching 1. So I'll guess that the limit of this function approaches 1 as x approaches 0. And actually, that's the right answer. But I can't use this as a proof, not as an argument. This is just evidence that it must be true. Unfortunately, the numerical method does have issues because of all the assumptions, and in the end we're guessing. To show you what I mean, consider this function, the sine of pi over x, and let's observe its behavior when x is near 0. So here is a list of x values that are approaching 0 and the corresponding function values. So as x is approaching 0, certainly looks like the function never changes. It's just always 0. So I would have to guess that the limit of this function should be 0. But I picked a finite sequence of numbers that approaches 0. Let's just pick a different one. So here's a different sequence of x values that are approaching 0. And this time the function's always 1. So based upon this chart, I would have to say that the limit should be 1. Well, but if the limit exists as x approaches 0, you can't get close to two different numbers. So I would have to say then, I guess this implies that the function has no limit. In fact, you can't even say that, because the list you used was a finite list. Maybe if we got even closer to x, the function would then, all the function values would get close to something else, like maybe a half. In fact, though, in this case, this limit actually doesn't exist at all. It's just that we can't use this technique to prove it. Obviously, the numerical method has some disadvantages. The large one would be, of course, that we're assuming the limit exists, and second, that we can observe the limit value by looking at a finite number of function values. One way to get around that is to look at the function's graph, because then we can kind of get an idea of all the function values all at once. So we assume that we can get a adequate graph of the function, and that from this graph we can define or determine the value of the limit. In this case, though, we are still guessing. So if you look at, I want to know what is the limit of the function of x plus 3 as x gets close to negative 2. The general process to find that using graphs would be to draw the line x equals negative 2. Pick two x values, one less than negative 2 and one greater than it. And for those x values, find the corresponding points on the graph. Then allow these x values to get close to what x is approaching, in this case negative 2. So then as that happens, you'll notice that the points will move on the graph but towards the vertical line. As they do that, as long as these points come to the same place in the plane, and that does not need to be a point on the graph, it just needs to be a point in the plane. Then, if that were to happen, you would be forced to assume that the limit exists and it's equal to the y-coordinate of that point. So, based upon this information, since that red point is negative 2, 1, I'd be forced to assume that the limit of the function x plus 3 as x approaches -2 is 1. Let's see if you understand what I've done. So look at this particular graph of the function I've given you, and I'm stating a limit of this function as x approaches 1 is 3. This is either true or it's false or you don't know. Why don't you pause the video for a second and see if you can guess which one's right. Alright, well, assuming that you did pause it, let's go figure it out. The answer is, yeah, this is actually true. Y is pretty straightforward. All you have to do is draw in the lines I mentioned. So if you look at the line, here is x equals 1, and then take an x value over here and take an x value over here, and find the corresponding points on the graph, and then let those x values approach x equals 1. Notice how you're getting towards this point right here, and that point is 1, 3. So the function values are approaching 3. Seems right. Okay, so let's try that again. Same function, all I'm doing is changing what x approaches. This time it's approaching -3. I'm claiming the limit is -1. Take a moment to determine, is this limit value correct? Is it not correct? Or are you still not sure? So assuming you've paused the video to think about it, the answer is actually this is true. Now why? If you look at x equals 3, well sorry, x equals -3, then pick an x value, and pick an x value, look at the corresponding points on the graph, and then let the x values approach x equals -3. You'll notice that the points on the graph are moving and move towards this open hole. Notice the point need not be a point on the graph. It just has to be a point in the plane. As long as these 2 points on the graph are going towards a single point in the plane, then the limit should exist. And it should be the y-coordinate of the point they approach. That point is -3, -1. So the function approaches the value of -1. One thing the graphical method does better than the numerical method is it gives you stronger evidence that the limit doesn't exist. That's just because the 2 points that we were discussing going towards the vertical line don't go to a single point. Also, this example is here to show you that function evaluation at a number and limit of function as x approaches those numbers are not the same thing. So I've given you a limit statement and I've given you an evaluation statement. One of them is wrong. Pause it for a moment and try to figure out which one's wrong. Okay, well, assuming that you did pause it, actually the limit statement's not true. In fact, the limit doesn't exist at all. The one on the right, this function evaluation, that is true. You can see it clearly right here as part of the definition. But the limit actually does not exist at all. I'll abbreviate that as DNE, does not exist. That's because if you look at the line x equals 3, pick an x value to the left of the line, pick a x value to the right of the line, look at the points on the graph when you do so, and let the x values approach the vertical line. The points stay on the graph and also, in this case, approach the vertical line, but they approach 2 different places. So then there can't be a limit, because if there was a limit, it would approach only one place. One last time, the graphical method really does give pretty good evidence that a limit value doesn't exist, because you're looking at all the function values at once. This limit here actually doesn't exist. The reason is if you go and draw the line x equals 0, here's x equals 0, winds up being the y-axis, and then pick an x value to the left and the right, and let those x values approach, in this case 0, and look at the corresponding points on the graph. The points on the graph in the right hand side go up without a bound, while the ones on the left hand side go down without a bound. Well, if there's a limit value, these things have to approach a point in the plane, and at least on one side or the other of this vertical line, they don't. So in this case, you would say the limit just doesn't exist. Later on, next video, we'll be able to describe how it doesn't exist. But right now, the only thing we can say is it does not exist. There is no limit value at all. So now we're up to the analytical technique, the best way to find the limit value of a function. It's the best way because it's using theorems. There's no way to get around it. If you use these properly, you get the right answer. It just takes a little bit of work. Also, it's counterintuitive because the limit laws require that you know that certain limits exist in order to find the limit of your function. All these limit laws do is take the limit of a really nasty expression and break it down into lots and lots of smaller limits. Hopefully all of those you can figure out what the values are. So, I'm sorry for what I'm about to do to you. Let's assume the limit of the function f of x and g of x both exist as x approaches c. Here are all limit laws for now. Oh boy, look at them all. Whew. So I'm going to verbally explain most of them, but I want to highlight a couple of them. The first one that you see right there is that the limit of a constant is a constant of a limit. The second one that you see there is that the limit of a sum or difference is a sum or difference of limits. And then you have the limit of a product is a product of limits, and so on. In all these limit laws, it basically says all you have to do is just push the limit law or push the limit operator through the operation that you see in the function. And then just take one limit and turn it into smaller limits. That can only be done, though, provided that all the conditions are met. All the new limits must exist. And in the case of the integer power, that the integer is a positive power, and that if you have division, that the limit of the denominator is not 0. And in the case of radical, if you have an even root, then the radicand, the function on the inside, that function must exist, or in this case, it must be at least greater than or equal to 0 for all numbers near c. Now, if that's not true, if the limit of the denominator is 0, that does not mean the limit doesn't exist. It just means you can't use these techniques. Now, those limit laws take big, nasty expressions and break them down into smaller, simpler ones. You hope to get one of these two, that the limit of x as x approaches c, because we can then just say that's c, or we can get the limit of a constant as x approaches c is just the constant. Let's try a couple examples. I want to know what's the limit of x squared minus 3x plus 5 as x approaches 2. So one of the limit laws is that the limit of a sum or difference is a sum or difference of limits. So I can push the limit operator into the different pieces here. So I have the limit of just x squared, then I have minus the limit of 3x, then as x approaches 2, and then I have plus the limit of 5 as x approaches 2. Now, the limit of a power is a power of limits. So that would then be the limit of x as x approaches 2. This will then be squared, minus the limit of a constant multiple is a constant multiple of the limit. So the constant can come out to get the limit of x as x approaches 2. And then you just have the limit of the constant, which here I'll just recopy over. Each of these new limits, we know what they equal. The limit of x as x approaches 2, that's just 2. The limit of x as x approaches 2, that's just 2. And the limit of a constant as x approaches anything is just the constant. So the answer then is 4 minus 6, that's minus 2, plus 5, that's 3. So the function values get as close as you like to 3 as x approaches 2. Well, what if you wanted to not do all this work? Just go right from the beginning all the way to the end. Do you see what you need to do? To find the limit, you just plug in the number. There's a very good reason for that. We'll explain that later. But for now, you can see that when you're doing the limit of a polynomial, the only thing you ever use is the sum, the difference, the constant multiple rules. And those rules have no conditions. Because of that, you can push the limit all the way down to eventually get the limit of x or the limit of a constant, which exists, and are found by essentially just evaluating the expression. So the limit of any polynomial is actually really easy. You literally just plug in the number. Let's try the next one. So I want to know the limit of this rational function. Well, to do so, I'll take the limit of the numerator and I'll take the limit of the denominator, because the limit of a quotient is a quotient of two separate limits. When I do that, though, I'm actually making a small assumption. I just haven't figured that if it's true or not. I'm assuming that this guy is not 0. See, I don't know if that's true or not. I'll find that out along the way. If the denominator is 0, that just means that I was never allowed to do what I just did. It just means I have to use a different technique. So if this denominator, this limit in the end in the denominator actually is 0, what I just did would be wrong. And I'd have to use something completely different from this point. But in the numerator, that's a limit of a polynomial. We know how to do that now. You just plug in the number. So that would be 3 squared minus 2 times 3 plus 1. And the denominator, that's the limit of a polynomial. You just plug in the number. So that would be this. Notice the limit of the denominator was not 0. Since it's not 0, I was allowed to use the quotient limit law. Therefore, I can say that the final limit is the denominator is 6. The numerator is 9 minus 6, that's 3, plus 1, that's 4. That is 2/3. So, the function's values get as close as you like to the value of 2/3 by restricting x to be close enough to 3. You should notice then that to find the limit of any rational function, provided that the number is in the domain of the function, the denominator would never be 0, which means you could use the quotient limit law. So to find the limit of any rational function, it's also really easy. You literally just plug in the number, provided it's in the domain. So I think that result that you just saw is important enough that you probably should see it written down for you, and also to see what it means in notation. So if you have any polynomial or rational function and you have a number in the domain of those functions, then the limit of the function as x approaches that value in the domain is the same as just evaluating the function. Notice that in this case, the limit and the function evaluation both exist and actually are the same value. You have seen in previous cases where that need not be true. So let's try it. In this case here, if I wanted to find this limit, notice that that's a rational function, and 3 is in the domain. So to find the limit, you just plug in the number. That would then be 3 squared minus 4. That's all over 3 minus 2. And that would be 9 minus 4, which is 5, over 1, that's 5. So the values of this function can be forced to be as close as you like to 5 by just restricting x to be close enough to 3. Let's try the next one. All right, so to find the limit of x squared minus 4 over x minus 2, but this time as x approaches 2. That's a rational function. So I just plug the number. But that's not what the theorem says. It says if you have a rational function and something's in the domain, then you just plug in the number to find the limit. That does not mean this limit doesn't exist. It means I can't use this technique, and I can't use the limit laws I've given you so far. Notice that if you were to plug in 0, you could think to yourself, don't say it equals, don't you dare say it equals. You can think to yourself, hey, this is of the form 0 over 0 when you plug in the number. Anytime you see 0 over 0, it's called an indeterminate form. Indeterminate forms, especially with limits, there's often some manipulation we can use in order to find the value of the limit. Let's go look at those examples. Well, to tackle these new limits that will get the indeterminate form, 0 over 0, we need another law. So the common one that we use is called the replacement or substitution theorem. In fact, some calculus courses never even give it a name. They just use it. It relies on the fact that as long as x is not c, if two functions have the same values always, except possibly when x is c, their limits have to be the same. Because in the limit, you never care about what happens when x is c. You only care about what happens when x is near it. So you could then say the limit of a function is the same as the limit of a different function because the two functions agree around c. Here's a sneaky way to use that. You look at this function and you take its limit. Notice if you were to plug in 1, the denominator is 0, but also the numerator is 0. So I would try using this particular theorem. I'm going to replace the function you see with another function that's equivalent to it except for the x values I care about. Now, notice the numerator can be factored, but x is approaching 1. That means the denominator is never 0. The numerator, x minus 1, that factor is also never 0. But that means those two factors are non-zero common factors. So I can cancel those particular factors to get a new function. And the new function and this function are not the same function. They'll have different domains, but they will be the same everywhere except 1. So the limits must be the same. So I can replace the old limit with a new limit. Well, the new limit is a limit of a polynomial. We know how to find that limit. We just plug in the number. So if you just plug in 1, you get the answer of -1. So the function values approach -1 as x approaches 1. Let's try that a number of times. The replacement/substitution theorem is used so often in limits that you really need some practice. So how do you know you should be using it? The first thing you should do is notice that in this case that you have a rational function. Just try plugging in -2 first. But if you do that in the numerator, you'll get 0. And if you do that in the denominator, you'll get 0. Don't you dare say it equals that, because this doesn't mean anything. You can say, I'm thinking it. That's fine. You can say, I'm thinking it has this value or has this form. So because of that, I have an idea or a hint that I should try using the replacement theorem. The replacement theorem basically boils down to cancel factors, almost always. Cancel factors so that you don't have a 0 over 0 when you plug in -2 anymore. So I will, in this case, take the numerator and factor out the common factor of 2. And in the denominator, I'll factor out the common factor. Well, at least I'll factor the polynomial to be x minus 1 times x plus 2. Notice then, this is the same as writing the limit. Since x is approaching -2, it never is -2. So the factor x plus 2, these factors, these are never 0, and they're common factors. So I can cancel them, resulting in an equivalent function for the range of values I'm interested in, which is everything but -2. This is now a limit of a rational function again, but this time -2 is in the domain, so I can plug in -2. I would get 2 over -2 minus 1. That would be -2/3. So this function's values can be forced to be as close as I want, too far, close as I want to -2/3 by just restricting x to be close enough to -2. Let's just try that again. This time you have not a rational function, but the ideas are the same. If you just use the limit laws, eventually you have to take the limit of the denominator. But to take the limit of the denominator, eventually you just plug numbers in, and you would get 0 in the denominator. But if you do the same in the numerator, you also get 0. This does not mean it equals this, and it does not mean the limit doesn't exist. It just means I can't use those limit laws, the simple ones, to get the answer. And don't you dare say it equals this. You can say, hey, I'm thinking this. I'm thinking that it equals that, it has that form. So I'll try using the replacement theorem. I want to somehow create some common factors and cancel them. So here the idea is to take the expression, since it has a radical, I'm going to take that denominator, I'm going to multiply by its conjugate. And I'll do that in both numerator and denominator. This is technically using the replacement theorem to put in factors. In the numerator then, do not distribute that product, just leave it alone. That would still be x minus 4 times the square root of x plus 2. while in the denominator, definitely do distribute that product. Because it has the form of a minus b times a plus b, the result is the square root of x squared, x, minus the 2 squared, which is 4. Notice now, x is not 4. So since x is not 4, in the limit, these two functions have the exact same values. I'll just cancel the common factor to give you the square root of x plus 2. That's because x is not 4. So x minus 4 is not 0. So you have a non-zero common factor you can cancel. I'm not claiming the functions are equal because they're not. They have different domains. But they do have the exact same value everywhere but 4. So their limits are the same, if they exist. To find this limit's easy. We just push the limit through. I'll go through this one slowly. That would then be the limit as x approaches 4 of the square root of x plus the limit of 2 as x approaches 4. And that would then equal the limit of a radical is a radical of limits. That would then be the square root of the limit of just x as x approaches 4. I can only do that if this inside limit is non-negative. And if it actually is 0, then you must be careful so that the function's values are always non-zero themselves, or else the function actually never existed for the values that we're looking at. And then you have plus the limit of 2 as x approaches 4. Each of these are easy to do. That's the square root of 4. And the limit of a constant is just the constant. That gives you 2 plus 2, and that is, well, that's 4. Notice that to find this limit, in the end, all I did was just plug in the numbers. That's because this function has 4 in its domain, and the function is defined to both sides. We'll talk more about this particular property to evaluate limits by plugging in numbers in the next video. Most importantly, though, the original function, I can force its values to be as close as you like to 4, provided that x is close enough to 4. One last example using this technique, basically the exact same idea. If you just to say plug in 0, notice the form that you get would be in the end, you'd have 0 over 0. This gives you a hint that you should try using the replacement theorem. So we're going to rewrite the function to somehow cancel factors. Specifically, I want to get rid of that x that's in the denominator. So I will take the numerator and I'll multiply by its conjugate. So you have the square root of x plus 1 minus 1, and I'll multiply that by the square root of x plus 1 plus 1, and I'll do the exact same thing in the denominator, multiplying by the square root of x plus 1 plus 1. This then equals, you get the limit as x approaches 0 of, in the numerator, that sets up a difference of squares. So I take the square root of x plus 1 and square it to get x plus 1. And then I subtract, I take 1 and square it, and I get 1. In the denominator, do not distribute this product. Just leave it alone, because I'm going to cancel factors in a minute. I need it to be factored. In the numerator, then the 1 and the minus 1 cancel. In the denominator, just leave it alone. Then you can say x is not 0. That means this factor of x is never 0. They're therefore also common factors. So I can cancel them because x is never 0. I'm not claiming the functions are equal. I'm claiming the limits are equal because the functions have the exact, they are equivalent functions on the range of values that I'm interested in, which is things near 0 but not 0. So that gives me 1 over the square root of x plus 1 plus 1. Now I bet you, if you think it through, you can see that in this particular function, I can find this limit by just plugging in 0, just by using all the different limit laws you've seen. So the answer is going to be 1 over, you'll get the square root of 1 plus 1. That is a half. And that's correct. This function, its values, can be forced to be as close as you like to a half, provided that I restrict x to be close enough to 0. Now, I don't want you to walk away thinking that you've learned all the limit laws. Oh no, there's more. But you've learned almost all the major ones. After this, it's just a matter of tweaking definitions a little bit to introduce different types of limits. So the squeeze theorem, though, is pretty one of the last ones. And honestly, you won't get a chance to use it very often, but you should understand what it means. So the assumptions, of which there's many, is to assume that you have three functions. A lower function L, an upper function U, and the function you're interested in, f of x. Assume that these functions all are defined on some open interval containing C, except possibly at C. We don't care if they're defined there or not. Also assume that the function values of L in this interval are less than or equal to the function values of f on that interval, which is less than or equal to the function values of L on that interval, and that the lower function's values approach a limit, the upper function's values approach a limit, and they're the same thing. I know, it's a lot of different conditions. If you have those things, then you can then say that the limit of the middle function is also L. Now, it's not hard to see why that would be true. That's because that if you look at the separate graphs, so here is the graph, let's say, of y equals L of x. Here will be the graph of y equals u of x. And all I need to do is make sure that f of x is between them. And here's the graph of f of x. So you have y equals f of x. Notice I had them all meet at one point. That's because, oh shit. Do you see how I had them all meet at one point? That's because I'm assuming that as x approaches a, that the limit of the lower function goes to a limit value, and the limit of the upper function goes to a limit value, and they're the same value. So of course, the middle function is forced, squeezed to go to the same exact place. Okay, so then in your homework, you're going to have almost none examples of where this can be used because it's very difficult to set up on your own. You're almost always given only one function, f of x, and then you have to come up with these other functions, L and U. So let's just start off by assuming that we have the functions. Assume you have that 1 minus x squared over 4 is always less than or equal to a function, which is always less than or equal to 1 plus x squared over 4 for everything near 0 except possibly at 0 itself. I want to know what's the limit value of the function as x approaches 0. Well, my answer would go like this. I would say, hey, notice that the limit of 1 minus x squared over 4 as x approaches 0, that's just 1, because that's just a polynomial. You just plug in the number. And at the same time, the limit of 1 plus x squared over 4 as x approaches 0, that limit is also 1, because that's just a polynomial. You just plug in the number to get the answer. So since the function values of f are trapped between these two functions, and the outer functions have the same limit as x approaches 0, then by the squeeze theorem, well, you have to get that the limit of the function, even though I have no idea what that function actually is, as x approaches 0, that limit must be 1 also. Now, the squeeze theorem is given different names. Squeeze theorem is traditional. It's been around forever, but it's been recently rebranded to be called the sandwich theorem. Then I think that's actually what most common books now use. But squeeze theorem, sandwich theorem is the exact same theorem. It's just a different name. So there you are. That's a basic introduction to what a limit is, how to investigate it, and the analytical technique using limit laws to find the value of the limit. We're not done. There's still more work to do with limits that I'll talk about next time.